Okay, good morning, everyone. Last Thursday, we have covered much material. We introduced the question that is any one of sine, cosine, tangent, cotangent, secant, cosecant are 1-to-1. So, so today we're going to get into the inverse function. But before we get to that, I think I want to cover the even function, odd function very briefly. Okay, so these are the two last concepts that I wish to cover before we get to the inverse trig function. Okay, so today we're going to first do even function, odd function. Okay, all right, definition, meaning of definition. So these will be the last two concepts that you are we're going to review. I believe most of you probably had it before, but how much we remember from the past, right? So we're gonna first review these concepts, and I start by definition. An even function, if, right? So we assume it is a function, even function, right? F. Okay, function F. Okay, so function F is even. Okay, you may like to put this on your flashcard. Is even if, okay, there's an if statement here, right? There's an if statement here. If what? If f of x or f of negative x is equal to f of x. Okay, for all x in the domain of f. Okay, so we're going to explain, we're going to talk about what about it, okay, why, what it means, right, what it means. You see, a lot of people get confused, okay, because odd function, the definition of odd function is this. Okay, just a change of a few words. If it's odd, if f of negative x is negative of f of x, right? So these are the two definitions of even function and odd function, right? When people look at these notation, they will say the negative sign is inside or outside. What's the difference? What is the difference, right? So that's the difference we want to explain. Okay, that's the difference we want to explain. Okay, so first of all, right, when we look at these two, f of a negative x, just in general, okay, just in general, before we talk about even function, odd function, what's the difference between these two? Right, the negative sign inside or outside, what's the difference? Well, here's the difference. We know that as a function, right, it takes input. Input is x, right? Input is x. And then after x is chosen, of course, from the domain of f, right? From the domain of f. But this also implies that if x is in the domain, negative x is also in the domain. Okay, so there's the implication of that. So implication is what? If x in the domain, it implies that if x is in, it implies negative x is in the domain. In the domain. Okay. So x is chosen, and then we're going to negate the x, negate it, right? Put a negative sign in front of it. For example, if x was 2, and then you make it a negative 2. If x was -5, then negative and -5 is +5. So x can be depend on what it is, what's the domain. That's if those numbers are in the domain, then you can just put a negative sign in front of it. It's still in the domain, that kind of thing. Okay. The negative x will serve as input. Okay. So f will be, the rule of f will apply to the input of negative x instead of x. And it produces output. That's the meaning of f of negative x. So you read it as, how do you read it? How do you read it? You read it as f of negative x. Okay, f of negative x. Got it? Now, what is negative of f of x? Well, this is how it's being processed. You first select x, and then you put into, oh, sorry, this should be negative x. Okay, sorry. And then you apply the rule function, and the output is f of x, and you put a negative sign in front of it, in front of the output. See, that's the difference. That's a difference. Okay, that's a difference. You guys follow me? So one is negate the input, then produce the output. And the other case is you produce the output and then negate the output. That's a difference. Then you say, are they always the same? Of course, they're not always the same. Of course, they're not always the same. For example, right? Suppose I have f of x equals to x squared, right? F of x equals x squared. Okay. So what I would do, suppose I would look at f of negative x. Right? To process this, we just have to replace x by negative x. And the result is going to be, you're going to square -1, and then you're going to square x. It's going to be the same as x squared. It's going to be the same as x squared because -1 squared is 1. Okay. In this case, f of x. Okay, so this is f of x squared. But this is f of x. I'm sorry. This is f of x. So in this case, f of x equals x squared. F of negative x is the same as f of x. So by definition, it is an even function. It is an even function, which we're going to talk about here. Okay, so let's look at another case. Right? So these are from the list of basic functions. Suppose we have x to the power of 3. Well, f of x equals x to the power of 3. So if we apply f of negative x, right? Everybody should have a paper pencil with you, okay? And then it's going to be equals to negative x to the power of 3. negative x to the power 3 is negative 1 to the power 3 multiply x raised to the power 3. And this is negative x raised to the power 3. What it means is that you're going to do the power first and apply the negative sign. So f of negative x is negative of x to the power 3. So now what's the relationship? Okay. Because x to raise to the power 3 is f of x, therefore this is just equals to negative of f of x. According to the definition of odd function, this guy is an odd function and this guy is an even function. So in some cases, right, these two processes produce the same thing, right? These two processes produce the same thing. Sometimes they produce the opposite. And then you'll be saying, well, are there cases it's neither, right? So even function, odd function. Okay, even function, odd function. Are there cases it's neither? Of course. There are cases that's neither. For example, I can create a function. This function, I will have x raised to the power 2 minus x. Okay, I just randomly pick this, function. Then I'm going to look at f of negative x, right? F of negative x. So negative x equals to, right? And x will be replaced by negative x squared minus x replaced by negative x. That equals to negative x squared is still equals to x squared. Minus negative x is plus x. Okay, so f of negative x does not equals to f of x. It does not equals to negative of f of x either, because this is negative of f of x, right? You just put a negative sign in front of f of x. What do we get? You put a negative sign in front of the whole thing, right? And then you apply the negative sign or distribute it, you get negative x squared plus x. So you can see f of negative x is neither f of x, right? You can, nor negative of f of x. Okay, therefore, thus we say this function f of x equals x squared minus x is neither even nor odd. So in general, we have these three categories of functions: even or odd or neither. Okay, even or odd or neither. Now, we just studied our trig functions, right? We just studied the trig functions. So before we look at our trig functions, odd, even properties, let's look at the geometric meaning, Okay, what is the meaning in graph? What's the meaning in graph, right? So that might be easier, but this is more visual, right? Let's go back to here. So algebraically, if you decide whether it's even or odd, you could just do these operations, right? You just, this has demonstrated it's even, this demonstrated it's odd, and you just have to apply the definition to it. And now let's look at the analytical geometry, Okay, let's look at the graphical aspect, the graph. We all know the graph, right? We all know the graph. So visual of even odd functions, even or odd functions. Okay, so what is the visual of it, right? First of all, let's look at the visual. We know this function is even. X squared is even. Do we know the graph of x squared? Everybody should know that, right? Everybody knows that. We've done the graph, we analyze the domain and range. We analyze the domain and range. The domain is all real numbers, right? The domain is all real numbers. Now, what it means, right? We know that this function satisfies what? It's even, right? It's even function, which implies that f of a negative x is the same as f of x. What does that mean? What does that mean? Okay, this is what it means. Okay, so I'm going to show you. Okay, so first of all, let's bring the picture, bring the tools of the picture, right? We first look at the input. Okay, we have two inputs, the input of negative x and the input of x. Okay, so what is negative x? What's x, right? What this says, if the input is negative x and the output is f of a negative x, on the other side, the input is x, the output is f of x. So what's the interpretation? What's the interpretation, right? So I'm going to use different colors. Let's use different colors. Okay, red. So this is, let's make this blue, right? Now, for the blue x, suppose this is x. This is a blue. What is a negative x? If x is blue, negative x, suppose I use green. The green is opposite of x, right? So it's going to be on this other side. So the blue and green are opposite. They're opposite numbers. Okay, that's what it means. X and the inputs are opposite to each other. You follow me? The inputs are opposite to each other. And what happened to their outputs? The outputs are the same. That's what it means. So even function basically tell us whenever the inputs are opposites, okay? Meaning one is -1, the other one will be +1, would be +1. And one is 5, the other one will be -5. Whenever the inputs are opposite, their respective output are always the same. So this is true for any inputs in the domain, which also imply that, you know, all the real numbers are in the domain. That's what basically means, right? Right? Makes sense? Because it means that if x is in the domain, negative x is also in the domain, vice versa. And not only that, when the inputs are opposite, the output are exactly the same. That's what it means. So that's the meaning of input function. In graph, what we see, we're going to see all of these dots, right? These two dots on the curve corresponds to opposite inputs, same output. And there are many, many more. There are many, many more. There'll be another pair. Okay, more pair, more pairs. Anywhere, everywhere. So you can see the consequence is that picture is going to be symmetrical with respect to y-axis. That's the basic feature of even function. Symmetrical. Okay, symmetrical to y-axis, right? You fold it along the y-axis, they overlap. So that's even function. So you can tell from the picture of even function, right? So now let's look at the trig functions we have seen. The trig we have function, we have done sine, cosine, tangent, cotangent, right? Which one of these have that kind of symmetry? Have that kind of symmetry?
Would it be all of them? Don't they all have the same?
All of them?
I mean, when I'm thinking about it in the graphs.
Think about those graphs. So we have the algebraic, and we also have the visual. You need to have both. You need to know both visual and the algebraic. And you're going to use this concept in calculus 1 and calculus 2. Okay, I think in chapter 5, calculus 1. Look at your notes. We have graphed, right? This is not a test. You guys look at the graph we have done. Look at the graph we have done. You guys got it, right? You guys got it what it means. Your sine, cosine, tangent, cotangent. Okay, so before, as you're exploring that, let's look at the odd function, f of x. Okay, f of x equals to x raised to the power 3. What it means. You know what? I think we probably should do some numbers. I think it might be a little difficult for you guys to see the x, right? With this particular function, right? What you see is that f of, okay, is Farouz there?
Yes, Professor.
Thank you. So let's just do a couple numbers so you guys have better sense, right? Because I just thought about if I do x, negative x, you may not have any idea, or you may not feel as comfortable. F of negative 2, even though this is not proof, this is just a verification, okay? And f of 2 equals to 2 squared. Okay, so I'm going to put it for example, right? F of 2, f of negative 2, right? So let me even make a table. So you guys work out that table just to see it for yourself. Okay, so this is x, and this is negative x. Okay? You guys have paper pencil with you? So your x is negative 2. F of x. Remember that column? F of negative x. Right? Let's do something that's more concrete. Okay, these are just some examples. Are you guys with me?
Yes.
All right, so I'm gonna give you a bunch of x. Okay, you're gonna work out the negative x, f of negative x. take an example. For the input of -2, negative of -2 is 2. So I'm going to do f of x, which is going to be f of -2, and that's going to be -2 squared. And f of -x, -x is 2, and that's going to be 2 squared. Okay, and this guy equals to 4, because -2 squared is -2 times -2. It equals to 4. 2 squared is 4. You guys see the example? I'm giving you 3, -5, two-thirds. Maybe one more. So I have chosen axes that can be positive or negative. Okay, because I don't want you to think x is always positive. Do you guys follow me? X itself may be negative. You need to get used to it. 5 classes in one. 5 classes in one. All right, so I'm going to give you one more number. -7. How about that? So could you guys do the operation, do the calculation, okay, for each one of those? Okay, last. I'm going to set you last. Okay, I also want you to write these mathematical notation. Okay, I want you to write these mathematical notation. F of -2 is the same as f of 2. You need to know these, you not only need to understand these notation, you need to be able to write them correctly. Okay, so if we need breakout rooms, we do breakout rooms. Shall we? Let's do that. Let's do this because I feel this might be more thorough. Okay, breakout rooms. So Farouz is there. Thank you, Farouz.
You're welcome, Professor. Yeah, I have access to breakout room. Anybody goes there, I will be jumping there.
Yeah. I want you to write the way I do here. Okay, because this exercise is to get you guys familiar with the notation, at the same time understand the notation. Okay, familiar with the notation, understand the notation, and can use the notation correctly. If we don't understand the notation, it's very difficult to understand the math. Very, very difficult to understand the math. Okay, so I draw this graph and I have those input, output separated. It's all to serve the purpose of understanding the notation. So we must make the effort to understand the notation. So I think this exercise is necessary, right, Farouz?
Yes, Professor, I guess you started with definition of even odd function, then you showed us visually what they look like. Even function is a happy face, I call it, x squared, f of x equals x. Then odd function, x cubed. So now you are bringing in the example algebraically with the numbers, so reinforce the concept. Right.
So we're gonna do odd first, odd later. Okay. So right now you just do the odd, do the even for me. Okay. And then, and then we're gonna do the odd after. Okay. Right now, just do this table and use the notation I have used. Don't take shortcut. Okay. Don't take shortcut.
Yes.
You're doing this for yourself.
I copied the table on my board, so if I see any students in the breakout room, I'm going to jump in breakout room.
Right.
Otherwise, I'm going to be by myself over there.
Thank you. Okay,
Yeah,
so everybody do it, okay? So I'm gonna be just one step behind you or a few steps behind you. So remember, this exercise is not about getting the right answer. It's about getting the right process, understand the notation, and be able to use the notation correctly. If you have any question, okay? So I hope this take care of people from all 5 classes with needs in all 5 classes.
Professor, I go to breakout room for a couple of minutes, see if anybody stop by.
Okay. All right, guys, I'm gonna close the room. Farouz is the only person there.
I'm here and I got the same table as you
Thank you.
got. Devin.
Thank you. You know, I mainly, you know, as I said, I want you guys to get familiar with the notation. When I was teaching calculus, a lot of time I found that the students who were in my calculus classes at the time, they have no idea about the notation. They have no idea about the notation, okay, some of them. So this becomes a very, very big obstacles for their success because they don't know what it means. They just put, oh, parentheses, open parentheses. As a matter of fact, every little stroke in mathematics, it means something. It means something because we use shorthand notation very much. Every stroke represents something. For example, after the name of the function, after the rule, right? We put parentheses. This basically tells us the input. This is the input. Okay. It also tells you the rule of the function depends on whatever in the parentheses. Okay. The rule of the function depends on X. If you don't understand these notations, for example, it's going to be even more difficult because in the future, when you're doing, you know, calculus 3, you're going to have X, Y, Z, you know, you're going to have X, Y, Z, you're going to have 3 variables. So this tells you the rule of the function depends on 3 variables, X, Y, Z. That's what it means. Mathematical notation are very, very consistent. You understand one, you understand all. You understand one, you understand all of this notation in similar nature. If you don't understand mathematical notation, I would say it's impossible to understand the subject matter at all. Okay, so with that said and done, okay, a lot of these notations, you just have to spend time to understand it. But the key word is that you need to spend time to understand it. Okay, you must spend time to understand it. But once you understand it, you realize that notation is actually pretty neat. It's short, it's brief, but it's very, very clear. It's very, very clear. There's no ambiguity. There's no ambiguity. Okay, there's no ambiguity at all. All right, so any questions about it? But all of these are examples. All of these are examples. They're not these are not proofs. Okay, just remember they're not proof. They're just examples. Okay, but when we went over earlier, we talk about, you know, f of x is even function. This is the proof. Okay, this is actually the proof. Right? If someone asks you to prove, right? Prove that it's even. Right? And this is the proof. This is the proof, even though the proof is very short. And of course, this is true for all real numbers. For all real number x. So that's the proof. Okay, and then that's the end of proof. Okay, and these are not proofs. These are not proofs. This is just examples of, you know, illustrated examples. But what it says, okay, so let's look at the visual. Let's look at the visual. Right, let's look at the visual. We just talk about the visual, right? When we talk about the visual, we talk about very briefly. Right? So I'm going to put this picture over here next to it. Right? We just operated on f of -2. So what does that mean? Right? What does that mean? So this is going to be -2. If this is -2, the opposite of -2 is +2. So this is 2. So these two pieces are opposite to each other. What are their output? F of -2 is this guy. Oh, wait. Okay, is this guy. And F of 2 is this guy. That's what it means. That's what it means. How about, how you guys follow me? Okay, so now how about 3, -3, right? 3, -3. So F of 3, this is 3. What is -3? -3 is on the other side. This is -3. And the output and their output. You see the input are still measured horizontally from the same point of reference, and the output is measured vertically from the same point of reference. Have that meaning changed? No, it has not changed ever since the beginning. You guys follow me? When you say -x, you should think of it's opposite of x, but x itself could be positive or negative. So that's what this table intended, right? Your x could be positive. If you the opposite of positive is negative. But if your x is negative, the opposite of negative is a positive. Right, so the same thing is for -5, +5, -7, +7. Do you guys get it? So we have the algebraic, we have the notation, and we have the visual. We have the visual. Okay. Are we good? So let's look at the visual. Let's look at these 3 aspects about the odd function. About the odd function. Okay, of course, I assume you guys are still thinking about, the trig functions, right? We'll get to it. We'll get to it. F of x equals x raised to the power of 3, right? And we know the proof. Okay, I gave you the proof. Earlier, right? So proof that is odd, right? So here's the proof. Here's the proof, right? And that's the end of it, right? So let's look at the visual. Right, the visual. And of course, we have done the picture, didn't we? You guys should know the picture very well, right? So this is the picture. Okay, so we're going to look at some numerical values. Let me make some adjustment about this picture. Okay, so that's a picture. I'm going to let it scoot over just a little bit. All right, so we have the visual. So let's look at some points. Okay, let's look at some examples. Okay, so we're going to do this table again. Okay, I'm going to give you the x. Are you going to figure out the -x, f of x? F of x. Two. F of -x, right? And then you're going to compare. And we're going to compare, right? So now I'm going to give you some values. Okay, I'm going to give you, say, -2, positive 3, negative, I'm going to give you a fraction, 2/3, negative 5. As an example, I will do an example. Okay, so negative, because x is negative, x itself is negative. So negative of the opposite of a negative 2 is a positive 2. So now I'm doing f of x. Okay, so when x is negative 2, this x is going to be replaced by negative 2. Input is replaced by negative 2. And negative 2 to the power of 3 is equals to what? 1, 2, 3 times. That's a negative 8. Negative x is 2. So f of a negative x is f of 2. F of 2 is 2 to the power of 3. Equals to 8. So f of a negative at 2 is a negative 8. F of 2 is an 8. So what do we see in this relationship? We saw that f of negative 2 is a negative f of 2. Do you agree with that? Because the output, when the input are opposite, the output are opposite as well. So if we put a negative sign in front of one of the output, it's going to be the same. Graphically, what it means on the graph. Okay. This is the input negative 2. The opposite is f of 2. Horizontal measurement from the same point of reference. The outputs for negative 2 is this guy. And the output for 2 is this guy. They are opposite. They are opposite. What it means is that if you put a negative sign for the one under, okay, so if I put, what it means is that if I put a negative sign in front of it, right? If I put a negative sign in front of the red here, this, the yellow is the opposite of the red. Okay, so this is 8, and this is a negative 8. So this will be negative 8 and negative 8. Or you put a negative sign in front of the red over on this side, and these two will be the same. That's what it means. You guys follow me? So you're reflecting the red over, you get the yellow, and these two are the same. So these two are the same. You guys follow me? Or did I make it, did I give you too much explanation? So we have the algebraic, we have the visual. We have the algebraic, we have the visual. And these two red bars are opposite to each other. So if you put a negative sign in front of one of them, they will be identical. Okay? All right, so now I want you to complete the table and go through the process. Go through the process. Farouz, you have anything in addition to what I just explained? I don't hear any responses. I don't know if everybody's with me.
Maybe it's just Monday and early morning.
Maybe just Monday early morning.
Yes.
Okay. Okay, guys.
Yes. It's the same thing, same concept, same process, just a different outputs compared to even function.
You have to put those. You need to be. You have to understand the notation as is related to what we understood before, and you see the consistency. But you also have to be able to do it algebraically. You must be able to do it algebraically in order to get those points in calculus classes. Are you guys with me? You can't say, oh, I understand, I see the picture, I understand, but you cannot do it on the paper. That doesn't help you. It helps you a little bit. Of course, it helps you if you understand it, but you have to be able to do it on paper by your own hands to get those points. Okay?
So, Professor, what I have seen in those classes, and I'm training myself for, higher level math, like calculus, so on and so forth, I see what you are trying to help us. And the higher level language is just the code, symbols. They're not going to explain every detail like a pre-algebra, those things. So, and this pre-calculus is absolutely helpful, useful, and we can complete that by practice. Practice makes it perfect, but faster, therefore easier.
I hope so. Thank you.
You're welcome.
I teach every concept in pre-calculus in the light of calculus classes, because I'm reflecting on how you're going to be using it, because I taught those classes many times. I knew what the student, what you might need. This semester, I only teach pre-calculus. Okay, but I already hear from my colleagues who are teaching calculus, and some of them are very frustrated.
Especially online.
Especially online. Yeah.
How about next semester, Professor? Are you going to teach winter, in the college? Some of your classes maybe 50-50 online, 50 in college?
I will not be teaching winter, but I'll be teaching spring, and I will be teaching half online, half on site, half in person.
And maybe it's too early to ask, do you have your winter session? Oh, you said you are not teaching.
No,
winter.
I have no
Okay.
winter classes.
All right.
No.
So
Yeah,
yeah,
but if you guys have questions, and I will make myself available to help you.
That's nice of you. Well,
My pleasure. My pleasure.
it's just I plan ahead of time for my next semester. Whenever your classes are, set, and if you wish, I'll be your in-class tutor. I don't know, pre-calculus, any 170 or whatever classes you teach. Please let me know.
Yeah, I have 2 sessions of pre-cal next semester. Yeah, I just saw my assignment.
Can you repeat one more time? Noisy here.
I'll type it. I have 2 sessions of pre-cal in spring.
Is it going to be in college or online? Do you know that?
One in person and the other online.
So that is perfect.
All right, guys, how are you doing? Did you guys manage to use the notation? Just use it, just be patient with yourself, right? So now let's see, input is a given input 3, the -3, right? The opposite 3 is -3, right? When you see -x in your mind, you should think of it's the opposite of x. Don't think of x is always positive. That's one of the pitfalls of a lot of our students. When they see x, when they see -x, right? -x may be positive or negative, just like x could be positive or negative. Are you guys with me? But one thing is certain, x and -x, they're always opposite. But it's not necessarily, there's no negative sign for x in front of it, it's going to be positive. No, that's not true, right? For example, a lot of students have hard time with this notation, which I'm going to bring this up again. I introduced this earlier this semester is because I want you guys to have the time to get it. Okay, I expect you guys to spend 6 months of your time to get over this. Okay, that's okay. That's pretty good. If you spend 6 months of this to get this, you are already winning. Because I have seen so many students in calculus class I taught. Okay, they struggle with this for most part of the semester and the following semester, and lose tons of points, and they had end up having to take the class again. That's why I give you this at the beginning of this semester. Okay, you need to resolve to get it. Sometimes you think you got it, sometimes you think you don't get it, because a lot of people are stuck here and say, isn't the absolute value is always positive? How come you get a negative sign there? Because x itself, when x itself is negative, in order to get that positive, you have to put a negative sign in front of that negative in order to get that positive. Because in this case, negative x is going to be guaranteed positive. And that's the only way to do it. Okay, so this expression, okay, I went over that with you. Okay, go watch the video. If you have questions, come back to me. So if you commit yourself from the beginning of this semester to the beginning of spring semester, and even during this time, you really understand this. And okay, of course, later I'm going to take this one and show you the variations of it, because in your calculus class, you're going to use the variation of it. Okay, it's not going to be always like this. They're going to have a change of phase. They have a little more complicated situation. If you get this, that will guarantee you have 10, 20 points, you know, in your advantage. Right, so without further ado, have we finished this table? Have we finished this table? So f of 3. Okay, so I assume you guys have finished. Okay, so that's going to be 3 to the power of 3, right? And that's 27. And this is going to be f of, whoops, negative 3. So that's going to be negative 3 to the power of 3. And negative 3 to the power of 3 is equals to negative 3 3 times, equals to negative 27. Right? So I hope these exercise really give you guys some hands-on, right? Equals to negative of f of 3. You know, in the first table I set up there, right? In the first table I set up there, so I try to reinforce this piece, right? I try to reinforce that concept of input-output. Right, this is x goes through f of x. You know, you negate you negate the input, and then you have the function process it, right? So negative 2/3, the opposite of a negative 2/3 is negative of negative 2/3. So that's going to be 2/3. Okay. So f of 2/3, I'm sorry, f of a negative 2/3, right? And it's going to be negative 2/3 to the power of 3. And that's going to be negative 2/3. And that's going to be negative 8/27. Okay. And f of 2/3. That's going to be equals to positive 8/27. Let me see if I can make the fonts just a little bit smaller so you can see everything without compromising the quality. Okay, so f of negative 2/3 equals to negative of f of 2/3. Oops, sorry. 2/3. Okay, so negative of negative 5 is positive 5. So f of negative 5, and that's going to be negative 5 to the power of 3. That's going to equal to negative 125. F of 5 equals to what? 5 to the power of 3. So what do we observe for odd function? Whenever the inputs are opposite, their respective outputs are opposite as well. Could I say that? Would you like to write it down?
Yeah, can you say it again or type it out?
Of course, I will type it out. Okay, so for odd function, so we observed whenever, where else did we learn about whenever? One-to-one function, increasing function, decreasing function, right? In the definition of odd function, even function, you don't see the word whenever, but there is whenever there. Okay, so whenever the inputs are opposite, their respective outputs are opposite. Do you agree? Opposite inputs, opposite outputs. Opposite inputs, opposite outputs. Do you see that? Do you see that? Do you guys see that? This is called observation. Observing. And this is true whenever. This is true always. So that's the feature about odd function. Can you say something to describe? Can you say something to describe the feature of even function? What would that be?
Would it be whenever the input are opposite, their output are the same?
That's right. That's perfect. Could you type it? Jacob, could you type that sentence on the chat so everybody can see?
Sure, but it's gonna be a while.
No problem. Take your time. That's wonderful, right? So you look at these features, you look at these definitions, okay? And you think about it and you put some examples of your choice and look into it. And you will find that you're going to observe so much more interesting phenomena, and you can write it using different words, Okay, so for even function, what do you say? Whenever the inputs are opposites, their respective outputs are the same. Okay, so we saw the numerical notation and we observed the phenomena. And now let's look at the visual, right? We did the visual for 2, -2. Can you do the visual for 3, -3? Even function, whenever the inputs are opposite and their outputs are the same. Yep. Okay, there's a little minor typo there, but that's okay. Very good job, Jacob. Okay, so now, so can you put these in the picture? Can you put these in the picture? For -3, 3 positive, 3 -3. Right, can you put that in the picture? Right? So this point, these 2 points, okay, so these 2 points, what do you see about these 2 points? Their inputs are opposite. This function is also a very important function that in calculus class we get to use it, okay? The inputs are opposite, right? And their outputs are opposite as well. Is that obvious? Is that obvious? Okay, so now we have the algebraic, we have the expression, we have all of these things about even odd function, but with the examples of our choices are basically from our basic 1 table, right? So let's look at our sine, cosine, odd even functions, right? Let's observe them. Let's observe them. The same concept, no difference. Right? So let's look at the sine. You graphed it, right? They're just as they are at our fingertips. They are at our fingertips. At our fingertips. At our fingertips. Right? So how do you know if it's even or odd or neither? Right? The visual would be, suppose this is my x. This is my x. What's the negative x? The negative x will be its opposite, right? Right, so this is x. That's a negative x. What's the output? What's the output? The output, there's one here. And there's one there. That's the visual. That's a visual. So that's a sine curve. From what you see, whenever the inputs are opposite, the output are opposite. Is that about right? About sine curve? Inputs are always measured from the same point of reference horizontally, and output is always measured from the same point of reference vertically. Has that meaning changed? No, never, and never will. Right? You will need this concept when you're in calculus 2, when you're doing the rotation of this and that. You still use this concept. You still use this concept, however basic and rudimentary it is, right? So is this true for sine? Yes, absolutely. Right? So this is the, sorry.
Yes.
You think you can write that down like whenever, like the part you said for that one?
Right, this is the sine, right?
Professor,
Yes.
do we need to mention within the domain of the sine function?
Domain is all real numbers.
I mean, a sine function to be a one-to-one, does it important to be one-to-one for sine function here?
No, sine is not one-to-one,
That's right.
right? Sine is not one-to-one. You can see it's not one-to-one, right? It doesn't pass the horizontal line test.
That is, yeah. So for all these even function, odd function, we don't need to worry about if this function is one-to-one or not.
No, well, even function is not one-to-one, okay? Some odd function are one-to-one, some odd function are not. Okay, so the relationship between even, odd, and one-to-one, that's a separate discussion. So right now we're doing just doing the even and or odd as even, odd per se. When we want to make that connection, we can have a separate discussion about it. You guys with me? So now we just talk about even function, odd function, the visual, algebraic, and the notation. You know, notation, visual, algebraic.
Thank you, Professor.
Yeah, but this function certainly is not one-to-one. Okay, so we just explored the meaning of even, odd. Okay, I initially thought we would probably just spend 10 minutes, but then I realized we may need more time for it. But that's okay. You know, the important thing is we understand it thoroughly. And I also show you the method of study. Don't forget, in the process of this instruction, I was trying to show you how you should study. How you should study, how I have studied. The details, the devil's in the details, right? So with this said and done, and then you say, well, you're just drawing a picture. I mean, your picture sometime on the paper is not even accurate, right? It's rough. How can you tell they're exactly the same? That's why we need the algebraic. We need the algebraic. So let's do the table. Let's do the table. Okay. So are you guys ready? I cannot just say, oh, look at this, look at that. This is the proof that sine is odd function. No, that's not a proof. That's just a visual. That's just a visual. To demonstrate to you it is an odd function, I have to show you a lot more. Okay, basically I have to show you to prove it. It has to be much more rigorous. But before we prove it, I want you guys to have some hands-on experience with it. Okay, so once again, right? So this is the function, right? So x, negative x, f of x, now you're gonna get to use your ARD. You get to use your ARD. You get to use your ARD. Okay, you got to use your ARD. So I'm going to give you some values. The first one I'm giving you is pi over 6. The next one I'm giving you is negative pi over 4. The third one I'm giving you is going to be pi over 3. The next one I'm giving you is going to be, this is you get to practice your ARD. Okay, you can even bring the unit circle to your application. Okay, so this is going to be negative and you guys do the rest. Okay, I'm going to give you an example. Okay, for negative pi over 4. Okay, for negative pi over 4, I'm doing something in the middle. Okay, for negative pi over 4, what is the negative of what's negative x, right? Because x is negative pi over 4, and negative x will be negative of a negative pi over 4, right? So that's going to be pi over 4, right? But what is f of x? What is f of negative pi over 4? All these notations are super important for us, for your learning experience. So that's going to be sine of negative pi over 4. How do you find out what's the value of negative pi over 4? Sine of negative pi over 4. You need to measure the angle from clockwise negative pi over 4. Yes, I want you guys to do it from the unit circle. Where's my unit circle? Come on, unit circle. Oops. Sorry. Right? We measure the angle of negative pi over 4 from the standard position, right? From here, and we terminate here. And you pick a point on the terminal size other than the origin. I'm citing the definition. And then this point, I decided I'm going to pick on unit circle. And that point is set, which is because the ratio is the same. You know, all of these thoughts we talked about before. So now sine negative pi over 4 is a blue number. And now what does it equal to? It equals to negative 1 over root 2. So equals to negative, if you like the other form, root 2 over 2. Does everybody follow me? And f of negative x, which is negative x, is what? It's pi over 4. So f of pi over 4 is equals to, f of pi over 4 is equals to what? Sine of pi over 4. Now everybody knows that, right? But you still need to have those ARD run through your mind, right? It's a counter clock measurement. You terminate over there. You see, this is how I want you guys to do the exercise. You just always do ARD whenever you handle trig function. In the end, you're going to be the master of it. If you ask me, there's any shortcut. This is the shortcut. This is the consistency. Do you guys follow me? Measure, right? Clockwise and counterclockwise measurement. Terminal, you pick a point on the terminal. You pick a point on the terminal side of the angle, right? You pick any point on it. Now I just pick up the point on the unit circle. That narrative has to go through our mind. When you train your brain like that, guess what happens? You always ace everything. That's what happens. Automatically. Okay. So of course you get the blue number. You may do this much faster than I do, because in time, that's going to be what's going to happen. That's going to be what happens to you. Okay, it's just a flush of thought. In fraction of seconds, ARD already went through your head. And that thoughts eventually will go through your mind like a nano speed. Okay, so now you can see the inputs are opposite. What happened to the output? The output are opposite too. But this is just one example, right? This is just one example. How do we express that? Algebraically? It's f of negative pi over 4. When you look at these mathematical notations, especially from the perspective of someone like me, as a student, you realize that these mathematical notations are so neatly designed. They're so sleekly designed. They're so beautifully designed. Okay, even for someone who, I told you, math is not my favorite subject, but you can't help it to start to really appreciate those mathematicians who have started using these notations. It's short, it's clear, no ambiguity, it's absolutely clear and logical. All right, so you're gonna continue to do the next. Are you guys there? So this should review and use. This should, get you guys to use the homework we assigned last week. You might even see a glimpse of your quiz, right? You might even see a glimpse of your quiz. Okay, so go ahead. Okay, do it with ARD. Do it with ARD. So at the beginning, it may take you 5 minutes to do ARD. And soon enough, it takes only 1 minute to do ARD. And soon enough, it's going to take you, nano speed for you to do the ARD. So getting the answer is not as important as how to get the answer. Right? So you complete the table, you realize whenever the inputs are opposite, the output are opposite. How do you express output opposites? This is how we express output opposites. Isn't that pretty cool, pretty neat? Right? So on the picture, you see that what happens? Negative pi over 4, positive pi over 4, right? They're opposite to each other. Negative pi over 4, it's probably about here, right? And that's pi over 4, that's a negative pi over 4. That's a negative pi over 4. They all measure it's horizontally measured from the same place, same point of reference, and their output are opposite to each other. Right? Their output are opposite to each other. Right? Now, from the unit circle, do we see the same phenomena? Do we see the same phenomena? Do we see the same phenomena that sign is odd? Absolutely. It's just a little more, it's just a little extra work, right? But it's a lot of fun. It's a lot of fun to see this, right? We understand the making of, right? We understand the making of it, the making of the unit circle, the making of the curve, right? We did those groundwork. Now, when we look at the angles that are measured, right? So opposite angle means what? One is measured counterclockwise, the other one is measured clockwise, right? Input are opposite, they're opposite angles. So if x is measured clockwise, negative x is measured counterclockwise, right? So for example, let me not use red. Suppose I'm using green, right? So I'm going to measure this angle. One is, I'm going to measure this angle over here. That's pi over 3. And then I'm going to measure its opposite. What's the opposite? Negative pi over 3. What happened to the blue number? The blue number is the same. I'm sorry, the blue number is opposite. Sorry, the blue number is opposite. Right? So our time is running up, but let's get started on cosine. Let's get started on cosine. For the same opposite angle, what happened to the red number? What happened to the red number? They're the same, aren't they? So in fact, the cosine is even. Cosine is even, okay? Cosine is even, right? So let's draw the cosine curve. Let's draw the cosine curve. Cosine. Is the cosine even? Is the cosine even? From the picture, you can tell, right? The input, opposite inputs. Right? And what's the outputs? Output the same. And from the unit circle, we just saw it, right? Whenever the angles are opposite, one is counterclockwise, the other one is clockwise, same measurement, their output are exactly the same. Isn't that even number, even function or what? Okay, so today I will give you the homework. I will give you homework, okay? You're gonna complete those tables. You're gonna complete those tables. Okay, you're gonna complete tables for similar, for sine, cosine, and tangent, cotangent. I'm gonna give you 4 tables in the homework, and these are outside the notes. Okay, so I'm gonna spell them out in the homework session for you guys to work with. Okay, and you will have a quiz on these. You'll have a quiz on these. Okay, in fact, your quiz, your last quiz, quiz number 12. I already used this concept. But you can do it. You absolutely can do it. You absolutely can do it. All right, is everybody with me?
Yes.
Any questions? Do you find this interesting? Do you think you have learned much today? Because we didn't get to cover the inverse function today. Right, we spent the whole time doing even odd functions. But I want to give you the visual, because you will see those notations in calculus classes. You will. I promise you, in chapter 5. Okay. So you have the visual, you have the definition, you have the, the numerical calculation, the visual and the algebraic. You need all of these. So one of the tables is going to be like this. Okay, one of the tables is going to be like this. Okay, and I will create a cosine table for you, a tangent table and a cotangent table for you. Okay, and I will put them all in the homework for you to view, and it just give me a little more time, because I didn't, when I create the notes, I didn't think of these exercise, so I just thought about it. This might be helpful for you. But anyway, without further ado, I will see you guys tomorrow. I'm looking forward to it.
Thank you, Professor.
Of course. Have a great day.
Ms. Wang, I have one quick question.